Anyway, I shall. Oh, I want to press now. Um, Now I'm recording, I think. Hello, YouTube. Hello, Zoom. Hello, Room. Um, we were. Let me just. Let me just pin Clemens, and then switch to one little frame. Um, okay. Where were we? There was a whole pile of stuff. What did we do? We defined this choose operation. So choose kn computes the number of ways to select k things from n. So what's the deal? If you're choosing no things, there's one way to do it. If you want more than one thing, um, then you better see how many things are available. If you want something and there's nothing available, you're host. If you want something and there's a first thing available, then you either say, well, I will choose the first thing and then one fewer from the rest because I've got one down already, or I'll reject the first thing and then I have to choose all the things from the remainder. So that's what our equations say. And then we sneakily rejigged our type of formula to include all the choosers instead of the variable. Of course, uh, uh, where we had x before, you can now write choose one, right? Because there's from x things, there are x ways to choose one. So we haven't lost any power, and we've actually gained a little. But because it's harder to define substitution, we have now built the shift operator directly into formula. And now our evaluate machinery interprets choose k as choose k, funnily enough, constants as constants, plus and times as pointwise plus and pointwise times, and shift by shifting. So that's to say, where was shift fun? Shift fun f of n is f of n plus 1. So we got all the machinery we need. I decided it was useful to have this definition of x to just remind us how to encode things. And if we want to do some examples, it's nice to have a short way of saying x. Okay. So then we were in the process of defining the forward difference operator for this new kind of formula. And we did the interesting part of the new case. We we waited to do the proof to see what the definition ought to be, and we realized that for choose k, we needed to split depending on whether k was 0 or more than 1. And in the 0 case, we discovered that diff of choose 0 had better be whatever it is you add to 1 to get 1. And that wasn't terribly tricky to work out. That means that it's constant 0. That's this line. And then, to our shock and delight, we found that the forward difference of choose successor of j, successor of something, is exactly choose j. So that's to say, all that happens is the number of things you're choosing goes down by 1 with forward difference. So this is to say that I don't know if you did differentiation at high school, you remember there was an easy way to differentiate x to the something. You multiply by the exponent and then subtract 1 from it. That thing. Well, Forward difference behaves quite nastily with powers of x, but the thing that behaves nicely is the chooses. So we're saying, yeah, there's a particularly healthy relationship between the choose function and the forward difference operator that we shall be exploiting. Anyway, what else happened? Uh, we left the constant case as before. You'll notice that the only change in multiplication is that we exploit the fact that we now have shift built into the language of formulae. We're doing the shift in the same place. We're just not doing it by substitution. We're coding it up directly. Okay, so um, there's a bunch of stuff here to do the old business. I think at the start of the lecture, as we are, I may well find myself just leaving the stuff that was the same as before uh, for offline attention because we really ought to pay attention to the new stuff, which is shift. Okay, so here we are. Here's our goal to figure out. We're trying to figure out what diff of shift q is. And whatever it is, it's got to make this equation true. Okay? But we can see at least some things here will compute. So let's line that up. And I'm going to hit accept and hope for the best. Okay. So, what have we here? We have evaluate q n plus 2 is what you get when you evaluate diff shift q and add it to q but n plus 1. Okay. So how am I going to make some progress here? I know I would quite like to persuade the left-hand side to be something plus this thing, right? Because then that something will have to be whatever diff shift q is. Giving myself a tongue twister. Okay, but cool. I have an induction hypothesis that tells me what happens when I evaluate q. So let's go by root. And I'm actually going to do the canonical thing. I pick up the goal. I paste it in here. Well, I want the right-hand side of the goal. Okay. And I am allowed to change P. I have to change P to something smaller than P. But we know that Q is smaller than P. And then here's the other thing, if you haven't got this message already, is that whenever you're using induction, the variable you're doing induction on has to get smaller. But the other variables, you can substitute anything you like. So in particular, I want successor of n instead of n. And that's an ugly thing. Have I got the bracketing right? I think so. Hit send. Hit accept. And now this looks like the stuff of an under plus. Okay. So let's hit accept and see where we're at. Right. So I have to make sure that that diff shift q uh, at n takes the same value as diff q at successor of n. But by definition, that's the same thing as that. And this is another fact that you may have encountered, which is important to notice. Sometimes you need to do this. You notice what I did was I just tweaked what the goal said. And ask didn't bother because computation is enough to show that what I want is the same thing as what ask wants. So it lets me have it the way I want it. And that did show up yesterday in the tutorial. Sometimes the need to do that. There was a problem where in order to do the right under plus move, you had to replace 0 by 0 plus 0. And ask is completely cool with that because ask can add. I mean, it's okay. So what this is telling us, straightforwardly, is that we had better define diff of shift q to be shift of diff q. Let's do that. And then we press send. And ask replies, why did you bother with all that rigmarole? It's obvious now. Um, but we had to bother with all that rigmarole to figure out how to make it obvious. Okay. I think I should probably, I'll post the code for the addition case and the multiplication case. If anything, the multiplication case gets slightly easier than before because the behavior of shift does the right thing by definition instead of by using some prior result about the behavior of substitution. So we've actually made it easier to prove stuff about this operation by baking shift into the language of formulating. But here we are. It's 10:24, and you can imagine what comes next. Where we're really heading is to take the next thing that we did for our formulae in our difference operator and port that to our new definition of formulae. Namely, we are going to figure out what on earth is going on with degree. So that's my real mission. I can zoom out a little bit. What's going on? Next week's tutorial homework is an exploration of the difference engine, which is controlled by an initial sequence of differences, where like in those examples we did a few weeks ago, where each row is made by adding on something from the row below. And you kick it off with an initial sequence of numbers. And the thing that tells you how long that sequence has to be is the degree, right? From the fact that if all you want is constant 0, you don't even need any differences at all. You're starting from zero and you're not moving. Um, Whereas if you're trying to generate a constant that isn't zero, then you need at least to say which constant it is. So you need one entry in the sequence of differences, and so on. If you're doing something linear, then you need two. If you're doing something quadratic, you need three, and so on. So we are heading in the direction of nailing that down. Uh, and yeah, your homework is going to involve proving a very lovely fact about the relationship between the difference engine and the choose operator. Um, and I think it's approachable. We'll get there. Um, so degree is going to be this important piece of machinery that tells us uh, how you know how far we have to go before we can stop putting more differences in the sequence. And the gnarlier the formula, the more differences you need. Okay. So it's the same thing. We want to make sure that um, uh, that when you take differences, degree goes down. So that the forward difference of quadratic things is linear, the forward difference of linear things is constant, the forward difference of constants is zero. And once you're at zero, you stay at zero. Okay, so let's go. Yep. Inductively P. As that's clearly, we're going to have to look at the formula to figure out what. Okay. And then it chooses terrible names. I'm going to call that K. That's C, Q, 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 R, R. Okay. So we also said last time that whenever you get a constant, you have to check whether it's zero or not. So I'm just going to fill in, let's fill in the boring bits. So the degree of zero is minus infinity. The degree of a positive constant is the number zero. And then the degree of Q plus R is the B max of degree Q, degree R. And the degree of Q times R is degree Q plus degree R. Story so far. Okay. Uh, let's do the next uh, the next most easy thing. What do you think the degree of shift Q is? If you think about what shift does to the graph of an operation, it just moves it sideways without changing the shape of it at all. So what do you think shifting does to the degree of a formula? Oh, oh, no, no. You're so I mean, if you take something linear and you shift it, you still have something linear. It's just that it starts from a different place, but keeps going up by the same amount. Um, so no, the answer is even simpler than what you're suggesting. What shift does to degree is absolutely nothing. So, and you can see that. I mean, if you also think about what happens, right? uh, if uh, uh, if if diff reduces degree, uh, then if and diff shift is shift diff, then shift better not do anything to degree. Okay. Next trick. What do you think the degree of choose K is? Let's have a little think about it. Remember, there's one way to choose zero things. So choose zero is the constant function returning one. What's that? What's the degree of the constant function returning one? It's zero, right? If we had said n1 instead of choose zero, uh, we'd certainly say that's degree zero. What about choosing one? How many ways are there to choose one thing from n? So if there are n things to choose and you want one of them, how many ways can you do it? N. Right. So choose one is linear. Likewise, choose two goes up quadratically. Um, and uh, and so on. And in particular, you know, because you proved it this week, that if you add up all the choose k's, you get to choose successor k's. Um, and yes, also, if you remember, uh, well, let's actually do it instead of talking about it. We try and prove this thing. We know we have to look at K. Um, this is J. All right, and then I'm going to say test for both of those, and let's see what comes back. See if we get any kind of a clue. Right. Um, so it's not completely decisive, but this is a couple of hints, right? We have to make sure that whatever degree we give to choose zero, uh, that um, uh, the minus infinity is one less than it. So that gives us two choices. And we already said we want the degree of choose zero to be zero. And if we take the predecessor of zero, we do get minus infinity. So that's going to work for this. Likewise, the degree of choose j had better be one less than whatever we choose the degree to be for choose j plus one. So that's to say, uh, uh, when when the number of choices goes down, the degree goes down. So I'm going to make the proposal that the degree of choose K is K, right? Choosing 0 constant, choosing 1 linear, choosing 2 quadratic. So it's this straightforward, that the degree of choose K is K. And I hit send. And then all of a sudden, Ask is extremely happy. Um, um, in fact, I'm not even sure we need we do need the from K, but it's fine. Um, okay. It is worth even though this kind of becomes revision for last week's tutorial. But yeah, I'll just you notice, by the way, that it didn't even generate a goal for the shift case. And that's because we really did say shift does nothing with degree. So the goal just turns into the induction hypothesis and is ask doesn't bother us with it. By the way, I am certainly running another help session today in Livy Tower 210 straight after this lecture. All very welcome. I've been hearing from Layla concerns that are being reported by people's personal development advisors that people are finding this module a bit of a struggle, and I'm hoping it's an active and productive struggle for most people, but for some people, it might just be descending into a learned helplessness funk. And I suspect that the people who are in that funk aren't in this room. But the advice went out. Also, some pleading from me to get hold of me and, get help. I'm all ears. Or your tutors or your pals. And so far, the number of people who have got in touch with me is a round number. So maybe we'll see who shows up in the help session today. But I digress. I was going to say, for a constant, we have to look at which constant. And then we're done. For addition, I will work through this by way of revision because I think it contains a useful teachable moment. But here we have Q and R, and then we're going to say test. And I'm going to put a bit of space in there. Hit send. Right. Okay. So, there's a couple of things that we need to hammer home here. We are you prove equations by taking little steps that make one side a little bit closer to the other side. And that's one reason why, for example, we give a damn about associativity because it allows us to fix brackets up. We give a damn about distributive laws because it allows us to bubble one thing past another. just to make things swim towards each other. That's why we bother with this structure. So here we see on the left-hand side, we've got degree diff Q and degree diff R, and we don't have any diffs on the right-hand side. So we need to focus on how to get rid of the diffs. And the main weapon we have in our arsenal is the fact that we know induction hypotheses for Q and for R. So our strategy is to say by root, and I'm going to pick up the left-hand side of the equation because that's what I'm going to take a step from. And then I'm going to pick up the right-hand side of the goal, and I'm going to paste it in over that thing, changing P to Q, and over that thing, changing P to R. And then I'm going to widen my window. Right. So all I've done is taken the left-hand side of the goal and replaced some sub-expressions by things I know are equal to those sub-expressions. Oops. So I know when I press send, I will get two sub-goals. There's the boring sub-goal, which just justifies my step with a bit of under B max. No, where did I? I pressed the wrong send button, didn't I? Okay, so that one's fine. And then we get the interesting sub-goal where we've got rid of diff. All we're doing is talking about degree Q and degree R. And we've got some kind of distribution going on relating B pred and B max. And we're in need of an aha moment, right? Because there was a move which we pulled in tutorials, and I'm going to try and teach you to learn to spot when that move is appropriate. Okay, so first of all, you can see that in this goal, the only way in which Q is involved is degree Q. And you can see that the only way in which R is involved is degree R. We are not relating degree Q to anything else about Q. We are not relating degree R to anything else about R, right? This is what I'm trying to suggest is that the use of degree in this goal might actually be a red herring. The other thing to observe, just to rub it in, is that degree of Q and degree of R could, in principle, be any botnum, right? All of the botnums are the degree of something. So if this is going to be true for all of the outputs of degree, it has to be true for any old botnum. Right? There's nothing, you don't learn anything about a botnum by knowing it's the output of degree. That doesn't narrow it down. What's more, we know that if we want to prove something relating Bmax and Bpred, talking about botnums, we are going to want those botnums to split neatly into cases, bot or num. We're going to want to actually make those things compute. That's to say, we want to we want to investigate the possibilities for the output of degree. That's what we're going to need to make progress. And at the moment, all our goal lets us fiddle with is the input to degree. So it's really tricky to figure out how to make degree Q split into bot or num by just looking at Q. It's not impossible, but it's somewhat indirect. So the right move is to say, look, this thing that we want, these degrees are a distraction. That's not meant to be a comment on higher education. So we can replace degree Q by a variable as long as we do so consistently, and degree R by another variable. And that gives us direct access to the things that are going to make the stuff compute. And it will be plenty to discharge our goal. What's more, as I said, degree Q and degree R, this statement has the same generality as the goal we wanted. It's just easier to work with because we know that degree Q could be any botnum, just like A could be any botnum. But now we're allowed to ask which botnum it is. So I will say here, given, and hit send, and then go back to this box. And now, hopefully, this is the traditional splatterfest from A. And then it makes up terrible names, which I'm not going to change because I'm running out of time. And I suspect I have to do from X. You notice no bottom case. X. Well, I'll do from B. So I'm going to have to. Right. And I've still got cases about numbers. I'll say, and I know some of these things compute, others don't. I think I have to do another split. And right. So it's just a splatterfest. We just had to split into the three possibilities, minus infinity, 0, positive, for each of the two variables. And then it just goes away. It goes away because we already know all of that stuff about ordinary max. So that was the key transferable lesson there, is how to spot when you need to yank a goal out and abstract bits and pieces from it that are really just a distraction. You find, or maybe you found that when you did the same thing for the multiplication case, you got another slightly gnarlier thing involving Bmax and triple plus and Bpred and lots of degrees that were getting in the way. That you again abstract and just beat to death, just splitting into the cases of minus infinity, 0, positive. Okay, so we've got our handle on degree. I will again finish off the cases that were the same as before. I think it was worthwhile spending lecture time looking at what's new. And I'm hoping to draw this all together in a neat little knot very shortly. So now I'm going to hit stop recording. Cheerio.